Hey guys, so today we are going to be discussing light emission in atoms. And so essentially what happened is that earlier in the 1900s, scientists observed that when they held elements in a flame or sent electricity through it, that it would emit a particular color of light. And each element emitted a different color. And this they found to be pretty consistent every time they did that, and so they related this phenomenon to that element's chemical behavior, and more specifically to the arrangement of the electrons. So what visible light is part of the electromagnetic radiation, part of our electromagnetic spectrum, because it exhibits wave-like behavior. We can use several characteristics to describe waves themselves. The first would be wavelength. We use this kind of upside down Y, but this is a Greek letter lambda to represent that. And what this is defined as is the shortest distance between equivalent points on a wave. Frequency is also represented with a Greek letter nu, and this is the number of waves that pass through a given point per second. And amplitude refers to the height of the wave. So again, just like we just said, wavelength is the distance between two identical points on a wave. Amplitude is the height of the wave. And then frequency is how many of these waves can pass through a point in a second. So the speed of light is a constant. It's known as being 3 times 10 to the 8th meters per second. We can find the speed of light by multiplying our wavelength by the frequency of the wave. Wavelength and frequency are inversely related, and what this means is that the longer the wavelength is, the lower the frequency. And if you think about this, it should make sense if you just look at these two colors. Red light has a longer wavelength than violet light does. So the longer wavelength allows the waves themselves to pass through a given point slower, thus resulting in a lower frequency because less waves can pass through. Violet light has a shorter wavelength, so more can pass through a given point, giving it a higher frequency. Sunlight itself has a continuous range of wavelengths and frequencies, and so if you take sunlight and send it through a prism, it will break it up into its component spectrum of colors. The visible light spectrum is a part of the electromagnetic spectrum that includes all forms of radiation. So this entire spectrum here, this is our electromagnetic spectrum. Only this very tiny portion here is what we can perceive, and that's visible light. So larger wavelengths are going to be things like radio waves. This is like how our cell phone towers work. Obviously radios as well. Microwaves are smaller than radio waves. And this is, we use microwaves to heat up food. Infrared waves are referring to the heat-seeking technologies. Visible light, again, this is the only part we can see. So these are all the colors of the rainbow. Again, we just, the red one is a higher, let me rephrase that. The red light is the longer wavelength than the purple or violet light. And so this one has a lower frequency here. After we get past the visible light are the types of radiation that can be harmful. So UV radiation, we know it can be harmful to our skin. X-rays also can be harmful. Granted, we use them, in a healthcare setting, but this is why you have to wear a lead vest. It's to protect your internal organs. And then gamma rays, these are not good for your health at all. These are very toxic radiation. Oops, I'm sorry. So we knew that light traveled in a wave, but it didn't explain all of light's characteristics. So Albert Einstein proposed that light not only has a wave-like property to it, but also has a particle-like property to it as well. And this particle that makes up light is called a photon. So the photon itself is a particle of light. It has no mass, but it carries energy with it. And that quantum of energy that it carries is this bundle of energy. Electrons in the atom can actually gain and lose energy by gaining or emitting photons. And so they gain or lose energy because these photons carry energy with them. And so a quantum of energy, again, is that bundle of energy that these photons carry with them. So if we were to determine the energy of a photon, the energy that a photon is carrying with it, we can use this this equation here, where the energy of a photon is equal to Planck's constant, so 6.63 times 10 to the negative 34 joules times a second, that's Planck's constant here, times the frequency of that wave. So this describes the photoelectric effect as well, which basically says that if a certain beam of light is emitted onto the surface of a metal, then an electron is ejected from that surface. Now we are going to apply this to the light emission spectrum. So, or we're going to see this in the flame test lab. But when you heat a specific element or you pass electricity through it, then it will excite the actual atoms or inside, meaning that the electrons will gain energy, so they jump energy levels, and then they emit light when they fall back down energy levels. And this is what we perceive. So this is how neon lights work. So if we take that light, so this is a hydrogen, this bulb here has only hydrogen gas in it. So if we turn it on and send electricity through it, it emits a very a certain type of light. If we take that light and send it through a prism, then it will break it up into its component wavelengths. We don't see a rainbow here because it's not sunlight. So sunlight has a continuous spectrum, but each element itself doesn't have that. It just has a very specific set of wavelengths. So hydrogen will always produce this wavelength of 410, 434, 46, 486, and 656. And because of this, we can actually identify anything out in the universe that's producing this as hydrogen. So this is kind of like a crash course of what happens. So we'll see this in a minute after we're done with this, I'm gonna show you a simulation that I've shown in class before with those notes. So electrons have energy level, or they're on energy levels. So if we have atoms closest to the electrons that are closest to the nucleus are at a lower energy level, and ones that are further out are at a higher energy level. And so they can move energy levels by gaining and losing energy in the form of a photon. So if you have an electron that is at a lower energy level, like closer to the nucleus, and it absorbs a photon, then it can jump to a higher energy level. When this atom releases that photon, it will fall back down in energy level. And when it releases that photon, then we perceive that as a flash of light. Each metal gives off a very specific spectrum of colors, and each element gives off a different spectrum. So for this reason, we can identify elements. So again, this is our emission spectrum here. If this light that we saw sent through that prism, and we get these specific wavelengths for that, that's what we call the atomic emission spectrum of an element. So it's that specific set of wavelengths that that element only gives off. Each element is its atomic emission spectrum is very unique, and so we can use this for identification purposes. I'm going to change the screen to a simulation. So this is a video that I recorded in class, and so just pay attention to the simulation. It's really useful in understanding this phenomenon here of light emission.